at the back. Okay, great. So, last talk of the day. I know you are really tired, but yeah, thanks for sticking. So, today I'm going to talk about how to hunt primordial black hole dark matter in the Lyman-alpha forest. And if you can't make sense of this title, don't worry, even Google Gemini can't. If you feed this title into Google Gemini, this is what it gives you, and this is absolute nonsense. But okay, is this better? Okay, but don't worry, I'll deconstruct each term in the title as we go on. And this work has been done with Akash Saha, whom you heard speaking today, Ranjan Laha, and Priyank Parashari, who is in University of Southern California now. Okay, so when we ask the question that what is everything made of in the universe, we get this pie chart that you have seen several times today. So most of the contribution comes from this part called dark energy, which drives the accelerated expansion of the universe. This is all the particles that we know and we know how to deal with, the standard model. Everything is just 4.9%. And then we have this other 27% contribution from what we term as dark matter. Now, dark matter behaves gravitationally exactly like ordinary matter, but as far as we know, does not seem to interact very much with ordinary matter through some other force. And yeah, the name of the game is to try to find out if dark matter has any interaction with standard model particles through any type of interaction, if it has, and then work out its properties. So the thing that we don't know about dark matter is what it's made of. And the answer, if you ask anybody what it's made of, is that nobody knows. And there are several guesses. In fact, I would say maybe too many, because we don't know where to channelize the resources at this point. But we know some things about dark matter. It's not that we don't know anything. One is that we know that it's around 5 times ordinary matter. And this 5 times, this ratio of 1:5 has not changed a lot during the history of the universe. This is important. The second thing we know is that it hardly interacts with baryons, hence the name dark. We also know that by now it is moving non-relativistic. And we also know that it is stable during the evolution of the universe, hence this 5 times number has not changed. And most likely, it's not made of the standard model particles. There are a few proposals here and there that maybe it's made of some bound states of quarks, but by and large, most likely it will turn out that it's made of something we don't know already. And we also kind of know how it's spatially distributed in the universe. In the large scale of the universe, in the scales of clusters, and in the scales of galaxies. There are small questions here and there that need some settling, but more or less we know how it's distributed. So that's pretty much, what we know about it. Now, but since we don't know its identity, we can ask the question whether dark matter is made of black holes. Now, do we mean black holes that are formed from the death of stars? The answer is no. Why? Well, I think my favorite lyricist, Irshad Kamil, explained this in this song. The point is that dark matter was there before any stars or any galaxies had formed. And since stellar black holes form after stars collapse, so black holes that form after the death of stars can't contribute to dark matter. But can we form black holes earlier? And the answer is maybe. Physics allows the formation of black holes very early in the universe. And there are various mechanisms for it. And these are called primordial black holes. And in fact, if you heard Akash talk today, he showed some constraints regarding these. And the point to note is that if they formed, then they definitely do contribute to dark matter. How much we don't know, but if they formed, they do contribute. Okay. Now, how to check this idea? Whether any primordial black holes were formed and how much they contribute to dark matter. Now, before I jump ahead, I just keep using these 3 abbreviations again and again. So, you already know primordial black holes, PBH. When I say DM, it means dark matter. This is new. Whenever I say IGM, it means intergalactic medium. And what this thing is? So this is just the dilute gas which is in empty but not so empty space in between the galaxies. And around half the baryonic matter of the universe is contained in this. It's not exactly bound to galaxies. And this is mostly hydrogen gas. Now, what's the idea? What's the key idea? The key idea is the following, that if dark matter is made of PBH, then PBH may emit Hawking radiation, and this Hawking radiation can heat up the intergalactic medium a little extra. By extra, I mean over and above all other sources of heating that IgM experiences. Now you go and measure the IgM's temperature. If it turns out that the IgM has been heated up extra, then you can start investigating whether that extra heating has really come from primordial black holes. But if it has not been heated up extra, then you can constrain the abundance of primordial black holes. Because if primordial black holes existed abundantly, then they would have heated up. But you find that it's not heated up. So that's the bird eye view of, what's the idea of the research. Now what about the Hawking radiation of black holes? I said that we try to detect the Hawking evaporation. So this is a famous formula that every black hole can be ascribed a temperature. And this formula is valid only for black holes that are not spinning. The important thing to note is that the temperature goes as 1 over m. Lighter the black hole, hotter it is. And this explains that why we have never thought of detecting Hawking radiation of black holes which are formed from the death of stars. Because they are at least a few solar masses, and for them the temperature is really small, so it's undetectable. But black holes that are formed in the early universe, they can be very light, and hence they can be very hot. And that is why we can have any hope of detecting their Hawking evaporation. Now, given a temperature of a black hole, what does it emit? It emits all the particles such that the temperature of the particle is, of the same order as the rest energy of the particle. Okay, that is all you need to know about Hawking radiation, more or less. Now, once you have a temperature of a black hole, then you need to, when you start to, look for the signatures that Hawking evaporation can have, you need to know the exact spectrum. And the spectrum looks like this. Now, if you ignore this part, this gamma something something, the rest of thing is just the black body spectrum, right? So, black holes evaporation is just like a black body emission, except for this factor. And why do these factors arise? They arise because, your light bulb does not have an event horizon, but a black hole has. It turns out that at the event horizon of the black hole, when particle-antiparticle pairs are spontaneously created, that's how Hawking evaporation works. Sometimes the particles do not reach the observer who's far away, and the particles get reabsorbed into the black hole. So this actually encodes the probability that a particle that's created as a result of the Hawking process actually escapes to an observer who's far away. And this calculation of these is not, simple, because what you are actually trying to do is you have to solve the scattering of the wave function of the particles that are created at the horizon in the curved spacetime of the black hole. So it's a scattering problem in curved spacetime. And so this has to be done numerically. And what we have done is we have used this code called Black Hawk to evaluate these factors. And once you evaluate these factors, you have the spectrum of the Hawking evaporation of black hole given a mass. So given a mass. And again, this expression is valid only for black holes that are not spinning. For black holes which are spinning, the expression is a little different, but the idea is same. And those factors can also be evaluated using the same code, which we did. Okay, now what Hawking radiation does to the IgM's temperature? IgM, remember, is intergalactic medium. So the temperature and ionization history of the IgM change over the evolution of the universe, throughout its evolution. And one thing to keep in mind is that although I told you that during Hawking evaporation all particles are emitted, allowed by temperature, but we need to consider only those, we need to consider only photons and electrons, positrons, because these are the only particles that actually can affect the temperature and ionization evolution of the IgM. And yeah, once electrons, positrons, and photons go into the IgM, they do various atomic processes, ionization, etc. happens. And we just, at the end of the day, the punchline is that they change how the temperature evolves as universe is aging. And just to throw in two symbolic equations. So we are solving for these two coupled differential equations. The rate of change of temperature of IgM has a background contribution from things that would have anyway been there, even if there were no evaporating black holes. Expansion of the universe and Compton scattering with the CMB, things like that. And this is the extra injection from the primordial black holes, the contribution to that term. And the third term is a little funny. This comes about because at some point, the universe formed stars and galaxies and AGNs and whatnot. And all these photons also escape into the IgM and heat the IgM, right? So we have to take into account that also. So this is the contribution from those sources. And this process is called reionization in astrophysics. So this is the contribution to the change of temperature by reionization, hence Re. And we have similar three terms for the ionization fraction, because these processes can ionize the IgM also. And these are coupled differential equations. The rate of, for example, this term depends on how much hydrogen is ionized, etc. And we have to solve these two coupled differential equations. And this again is a numerical problem, and we do this using this code called dark history. Now dark history was meant to solve this problem for dark matter particles that were annihilating or decaying. We modified the code so that it could incorporate the Hawking spectrum of evaporating primordial black holes. We did this and then let dark history do its job. And we obtain the temperature as a function of redshift. Z stands for redshift. And people who are not familiar with redshift is just like it's like the time of the age of the universe in reverse. So higher the redshift, younger is the universe. Basically, we get temperature as a history of as time goes on in the universe, how the temperature of the intergalactic medium changes. That's what we obtain. But how to measure the actual temperature as a function of redshift or as the universe is evolving? To go back to this slide that I showed earlier, I have covered this part of the overall idea. The dark matter is made of black holes, they Hawking radiate, and this heats up the intergalactic medium. Now we come here. We have to measure the IgM's temperature and then decide whether, maybe we have detected primordial black holes or we can constrain their abundance. Now, how to measure the temperature? Go back to your class, I think 12 NCRT. So there's this Lyman-alpha transition that happens between n equal to 2 and n equal to 1 levels of the hydrogen atom. And this is the most ubiquitous transition that's valid for hydrogen atoms. And yeah, it's in the UV band. Yeah, these are some characteristics of the line. And it's actually a doublet, not a singlet. Spin orbit coupling. Okay, but the important thing for us is that we can use this line spectroscopy to measure the temperature of the intergalactic medium. And what's the key idea? So suppose you have a quasar. So that thing over there is a quasar. Quasar is a very massive black hole that has, a disk of accreting material going around it, and it emits electromagnetic radiation with a very broad spectrum. So pretty much, many wavelengths are there in it. It's a very broad and continuous spectrum. Now you see what happens. As the light from quasar comes to us, it passes through clouds of neutral hydrogen. Why do I say clouds? Because by this time, intergalactic medium has started to get ionized, but there are clouds of neutral hydrogen left here and there in between. So as the light from any quasar comes to us, it passes through, just by chance, some clouds of neutral hydrogen. And because neutral hydrogen can cause this Lyman-alpha transition, we'll see an absorption line. But we'll not see an absorption line at a single wavelength in the quasar spectrum. We'll see many of them. The reason is the following. As light travels in the universe, its wavelength gets stretched. This is called the redshifting of light. Right. So suppose in this cloud, this wavelength gets absorbed. But by the time the light from quasar comes here, it has redshifted. So wavelength, the photons of this wavelength can't cause Lyman-alpha transition here, but photons of a higher frequency, or wait, yeah, lower, whatever. I know you get the point. It gets redshifted, and by the time it comes here, it can cause the transition, right? And hence, when you look at the quasar spectrum as a whole, you see series of absorption lines. For example, these. And the width of these absorption features contain the information of the temperature of the gas. So you get temperature here, 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 everywhere. Right. And by the way, this is why we call it the Lyman-alpha forest, because these lines are supposed to look like trees. Since there are many trees, hence it's called the Lyman-alpha forest. And this is how the actual spectrum looks like. Just look at the lower panel. Okay. So astronomers do this. They have this Lyman-alpha spectra. They measure the temperature of the intergalactic medium at various redshifts. And these are the data points that they get. Try to ignore everything else in the plot at this point. Just focus on these data points. So this is temperature on the vertical axis. Horizontal axis is the redshift. So this is present. This is past. As you go along this direction, you go towards past. As the universe evolves in this direction. Now, if there was dark matter that was made of primordial black holes of mass 10 to the 16 grams, and if these black holes contributed a fraction 0.5%, 5 times 10 to the minus 3 to the total density of dark matter, then what would the temperature evolution of the intergalactic medium look like? And the answer is this line, this greenish, bluish, teal colored line. And clearly you can say that since this model of dark matter with these characteristics is overheating the intergalactic medium, this is not allowed. Okay. Now you can play this game again and again for various masses of primordial black holes and various contributions of it to the total dark matter density. And then you can just check which models are allowed and which models are not allowed. And once you play this game, this is what you get. On the horizontal axis, I have the mass of the primordial black holes in grams. Notice that these are light black holes, 10 to the 16 grams, 10 to the 17 grams. Sun is 10 to the 33 grams. And on the vertical axis, I have this parameter FPBH, just the contribution, the fraction of the dark matter density contributed by the primordial black holes of a given mass. And the shaded region is ruled out. For example, if you consider that maybe there are 10 to the 16 gram primordial black holes present in the dark matter, then you can say that their contribution by our analysis can't be more than around 10 to the minus 3. This is how you read this plot. The shaded region is ruled out. The other lines are the limits obtained by other people using various other techniques, and these are the lines that Akash also showed in his talk today. Now, why is there not a sharp line, but there are regions? I mean, why are there bands of, limits? The reason is the following. Remember I told you that we have this term T dot Ri, which takes into account the fact that there are stars and galaxies also forming in the universe, and they can also heat up the universe, which I called contribution from reionization. Now it turns out that this process of reionization is not very well understood. There are lots of uncertainties hanging around in its understanding. Now you can take two approaches. One is that you can say that I'll be very conservative, very cautious, and I will just not take into account the contribution from reionization. In that case, I will get very conservative bounds in the sense that my limits will be weaker, and this is these limits. They are weak limits, but they are completely immune to whatever reionization physics actually is. The second thing you can do is you can be a little brave and you can say that, okay, let us try to model reionization in some way. Now, because the model, there's a lot of variation in the models, so you will get a lot of uncertainty in your limits, and hence this broad band. But because now you have somehow taken into account the contribution from reionizing sources and hence your limits are a little stronger. Now, as I told you that the Hawking spectrum of evaporating black holes depends on the spin, and these limits are valid when all the black holes are not spinning. You can ask what happens when they are spinning. If there's one thing that you should know about spinning black holes, it's that if they are spinning, they evaporate slightly faster. They inject more energy. And hence, if they inject more energy, then the limits should be a little stronger, because then a given mass primordial black hole will even more heat up the intergalactic medium. And once you allow for the spin of the black holes, these are the limits. And this is what's called the spin parameter of a black hole. So it can vary from 0 to 1. So this is the maximal spin that is allowed for any black hole. Yeah, so this is the summary. I'll just leave you to read it. Thanks for listening.
Questions?
Thank you for this great talk. So I have some questions. So first one is, so if the IgM temperature increases, that will have an effect on the star formation efficiency.
Yes.
So can that be probed using the HST data or JWST data?
No, so the thing is that stars form within the galaxies.
Yes.
We are talking about intergalactic medium.
Yes.
So I don't know if there's a lot of effect.
Okay.
To first order, there should be no effect.
Okay. So if there is a mass of the primordial black hole, there is a Schwarzschild radius that is associated with it, and depending on the Schwarzschild radius, that decides that what is affected. If it's intergalactic medium or inside galaxy, is that the thing?
No. Maybe I completely, I said something not comprehensible. So the point is the following. You say that stars formation should be affected. What I'm saying is that stars are forming inside the galaxy.
Yeah.
And I'm talking about whatever is happening in the dilute gas within two galaxies. Mm-hmm. Now, if I'm injecting some heat there, sure, there should be some feedback, but there should not be a lot of change.
Okay.
Because stellar formation, even though the process is not understood at this point, but to zeroth order is affected by what's happening inside the galaxy.
And my second question is, so for this you have considered monochromatic mass of primordial black holes.
Yes.
So can this be modified if we take a distribution of primordial black holes with some average mass with a given sigma of primordial? So these results will be modified then, right?
Yes. They will be modified, but the change is not a lot. So in general, what happens is, for example, here, so suppose if you take a distribution, you say that all the black holes are not of this mass, but some of them may have this mass also, right? Let's take a bimodal distribution. Now, when I was computing the limits just from this, right? So in that case, I will just take the Hawking spectrum from this as well as this. So the limit here will, so the limits sort of just spread out a little bit. They become weaker, but they start to spread out horizontally. Yeah, to first order. But you can ask, that the Hawking evaporation in this case is weaker than in this case.
It doesn't have to be bimodal. It can be a Gaussian.
Yeah, this is just an example.
Broad width.
The general lesson is, if you take a distribution, the limits become weaker or stronger depending upon how you tweak your distribution, and they spread outwards a little bit.
And instead of temperature, so is there a plot for the optical depth because of this?
Optical depth of what?
Optical depth of electrons. So because there is, or photons, because there is more temperature, more ionization. So this should change, in principle, change the optical depth of this system, right?
Yeah, we have I don't have it right now, but we have a plot of how the ionization fraction changes.
Okay.
But so that will have an effect on optical depth, but we have not computed it.
Okay, thanks.
Yeah, but the ionization fraction can be easily computed.
Yeah, thanks.
So basically in your formula for that rate of emission, there were two symbols L and M also.
Where? Here?
Yeah, the L and M. So can you explain what these are?
Okay, good. So I told you, right, that actually what you're doing is the wave function of the quantum particle is scattering in the gravitational field of the black hole. Now, when I say wave function, the wave function, just hydrogen atom, you expand your wave function in, spherical YLM. So this is just this, the quantum numbers that come with the wave function of the particle you are considering. So these are just, the YLMs of hydrogen atom, for example. So wave function has been expanded into a basis, a spherically symmetric basis for non-spinning ones.
Yeah, so the alpha that you talked about, alpha you said that it is, the maximum can be 0.999 something like that, right?
Maybe not alpha.
What was this alpha, right?
This.
Yeah, A.
Yes.
What was this value? Like, this is very close to extremal black holes? Like,
Yeah, this is 0.9999.
But can't the black holes be extremal? So what happens to the extremal black holes?
No, extremal black holes, I think the Hawking evaporation completely stops only, as far as I know. I'm not sure, but I think the extremal black holes don't evaporate. Yeah.
Why wouldn't they?
Yeah, but because they have entropy, right? But entropy is still finite, right? They can still have evaporation. The temperature is zero, but
External black holes are stable completely.
Yeah.
Well, I've got this, but you actually know better than me. Pretty sure external black holes are completely stable.
Abhijeet, thank you for the nice talk. And also, I would like to thank all the speakers of the section, and that conclude these sections.